Hold up your hand. Just look at it for a moment. The skin, the tendons beneath, the faint blue lines of veins if you tip it toward the light. You have done this 10,000 times without thinking about it. But I want you to do it once while knowing something that most people go their entire lives without truly sitting with. The hydrogen in the water molecules between those cells is nearly 14 billion years old. It was made in the first 3 minutes after the Big Bang. It has been waiting in that form, that particular arrangement of a proton and an electron, longer than the Earth has existed. It was here before the sun, before the solar system, before the galaxy had settled into its current shape. And now it is in your hand. The oxygen that hydrogen is bonded to was made inside a star that died before our sun was born. The carbon in every one of your cells was forged through a process that almost didn't work, through a piece of physics that had to be exactly right and that one physicist predicted from pure logic before anyone had tested it. The iron in your blood, every molecule of it, was made inside the collapsing core of a massive star. That star had to die to make you. The calcium in your bones was smelted in a stellar explosion that happened and was over before this planet existed. You are not made of Earth. Earth is just the address where the cosmos left you. I keep coming back to that thought. I've read a lot of science books, and most of them leave me with something to chew on. But this particular thread, what you are actually made of and where those materials come from, unsettled me in a way I didn't expect. It got under my skin. Not as a metaphor, literally. Because the book that sent me down this rabbit hole is one of the most famous science books ever written, and its central argument is so simple and so well verified that I don't know how it hasn't permanently changed the way everyone thinks about themselves. The book is called Cosmos by Carl Sagan. It came out in 1980 as the companion volume to his 13-part television series, and it has been in print ever since, which tells you something. Sagan was a scientist at Cornell who spent his career studying planetary atmospheres and the conditions for life in the universe, and he had a gift, rare among scientists, for taking verified, documented, settled astrophysical fact and making you feel the weight of it in your body. There is a line in Cosmos that I want to get to. 2 lines, actually, short ones. Sagan wrote them as summary statements, not as poetry, though they have been quoted as poetry ever since. But before I give them to you, I want you to understand why they are true. Because the story behind them is longer and stranger and more dramatic than the lines themselves, and knowing the story is the thing that makes the lines land the way they're supposed to. This is going to take a while, and it is worth every minute. Let me start 13.5 billion years before your hand existed. The universe is 3 minutes old. Not 3 million years, not 3,000. 3 minutes. The temperature is roughly 1 billion degrees. The entire observable universe, everything that will ever become galaxies and stars and planets and you, is compressed into a space so hot and dense that the ordinary rules of chemistry don't apply. There are no atoms yet. There are only protons and neutrons and electrons and a staggering amount of energy, and they are smashing into each other faster than anything you have experienced. In this 3-minute window, something happens that will never happen again. Nuclear physics gets its one unrepeatable experiment. Think of it as a forge that reaches the right temperature exactly once and then cools forever. Protons and neutrons are flying into each other at velocities that allow them to fuse, to stick together and form nuclei. But the window is narrow. The universe is expanding and cooling, and as it cools, the collisions slow down, and eventually the temperature drops below the threshold where fusion can happen. The forge closes. Whatever nuclei exist at that moment are the nuclei you get. And here's the thing. The forge closes too fast. Most nuclei don't have time to build up past helium. The 3-minute window is enough for protons to fuse into hydrogen, for some hydrogen to fuse into deuterium, and then helium, for a trace of lithium to form. And then, nothing. The universe has produced roughly 75% hydrogen and 25% helium by mass, with traces of a few lighter isotopes: no carbon, no oxygen, no iron, no phosphorus, no calcium, no nitrogen, no sulfur. Every element heavier than lithium is absent from the universe, completely absent. The cosmos, at 3 minutes old, does not have the ingredients for life. It doesn't even come close. This is the starting point: hydrogen and helium in the dark for hundreds of millions of years. This is what scientists call the dark ages of the universe, a period before there were any stars, when the gas was drifting and cooling and slowly, very slowly, beginning to clump under gravity. It was a universe of nearly uniform hydrogen fog, restless and structureless, with no light sources anywhere, no stars, no planets, no anything. And then gravity did what gravity does. It pulled. Slowly at first, then faster, as overdense patches drew in surrounding gas, grew heavier, pulled harder. The hydrogen fog began to gather into filaments, then into clouds, then into the first protostars. Spheres of gas so massive that the pressure at their cores reached a temperature at which hydrogen nuclei began to slam together hard enough to fuse. The first stars lit up. They were nothing like the sun. They were enormous, some of them hundreds of times the sun's mass, and they burned fast and hot and died young, as massive stars do. But inside their cores, something was happening for the first time in the history of the universe. Hydrogen was being turned into helium. Helium was accumulating in the core as hydrogen was depleted. And when enough helium had gathered, and when the temperature climbed high enough, the core began to do something that the Big Bang had not done. It began to fuse helium into heavier elements. The first new atoms were being made. The periodic table was being written, element by element, inside stellar cores, by nuclear fire. Now I need to tell you about a man named Fred Hoyle, because without understanding what he did in 1953, you do not understand why any of this matters for your hand. Hoyle was a British astronomer, contrarian by nature, brilliant by training, and in perpetual low-grade argument with the scientific establishment. He did not believe in the Big Bang, actually. He coined the term mockingly in a 1949 radio broadcast, meaning to ridicule the theory. The irony that the name stuck and became the standard term is one of the sharper jokes in the history of science. But whatever his cosmological views, Hoyle understood stellar interiors better than almost anyone alive. And in the early 1950s, he was working through the question of how stars build heavy elements. The problem he ran into was carbon. Carbon is the backbone of every living thing you have ever seen. Every protein, every strand of DNA, every cell membrane is built around a carbon skeleton. Life, as we know it, is carbon-based chemistry, which means that if the universe can't produce enough carbon, biology is simply impossible. Hoyle was trying to trace how carbon formed inside stars, and he kept running into a gap in the physics. Here's what you need to know about how stars make carbon. Inside a stellar core hot enough, helium nuclei, each one made of 2 protons and 2 neutrons, can collide and fuse. 2 helium nuclei make a beryllium-8 nucleus. The problem is that beryllium-8 is unstable. It falls apart almost instantly, in less than 100 millionth of a billionth of a second. So for carbon to form, a 3rd helium nucleus has to collide with that beryllium-8 and fuse with it before the beryllium falls apart. The odds of that happening fast enough at stellar temperatures seem vanishingly small. The numbers don't work. When Hoyle ran the calculations, the process, called the triple alpha process because it involves 3 helium nuclei, which were then called alpha particles, should be far too slow to produce the carbon abundance we actually observe in the universe. There's too much carbon everywhere you look. The stars aren't making it fast enough, unless there's something the calculations are missing. Hoyle had an idea. He thought there might be a shortcut, a quantum mechanical property of carbon-12 that he called a resonance state. You can think of a resonance state as a kind of quantum turnstile. Atomic nuclei can exist at specific energy levels, like rungs on a ladder. If a resonance exists at the right energy level, it acts like a door that swings open when the incoming particles arrive at exactly that energy. The collision passes through instead of bouncing off. The process speeds up dramatically. Hoyle calculated that for the triple alpha process to produce carbon at the rate the universe actually produces it, carbon-12 would need to have a resonance state at almost exactly 7.65 million electron volts. Not 7.3, not 8, a very specific energy. And as of 1953, no one had ever measured that resonance. Physicists who had studied carbon thoroughly had no reason to think it was there. He went to California. He walked into a nuclear physics lab at Caltech and told the experimenters there was a property of carbon that no one had found yet, and that if it didn't exist, none of us would exist either. The team initially pushed back. They had studied carbon. But eventually, a junior physicist named Ward Whaling ran the experiment. The resonance was real, almost exactly where Hoyle said it would be. Let that land for a moment. A man deduced, from the fact that biology exists and carbon is abundant, that carbon-12 must have a specific quantum property, and he was right. The universe had arranged itself such that helium nuclei could build carbon. Without that resonance, without that particular quantum shortcut, the triple alpha process would be too slow. Carbon would be vanishingly rare, the universe would have stayed hydrogen and helium and a little lithium, and the periodic table would have stalled at helium, and you would not exist to read anything about any of it. I want to be careful here. Some historians of science have pointed out, carefully and convincingly, that Hoyle may not have been making an explicitly philosophical argument at the time. The prediction itself was astrophysical, not metaphysical. He was solving a production rate problem, not meditating on existence. But the prediction was verified, and the physical fact stands: carbon only exists in the abundance it does because the quantum mechanics of carbon-12 happen to work out exactly right. Whether that observation says something profound about the universe, or is simply a fact we should note and move on from, is, as Hoyle himself might have said, a matter of interpretation. What is not interpretation is this: carbon exists in your body because of the triple alpha process, which works because of a resonance state at approximately 7.65 million electron volts, which was predicted in 1953 by an argumentative British astronomer who was wrong about the Big Bang and right about this. Now, the story moves from one man to four. In the years after Hoyle's carbon prediction, a question that had been floating around astrophysics began to feel answerable for the first time. The question was, where did all the elements come from? Not just carbon, every element, the entire periodic table, hydrogen through uranium. Each of these elements is found in stars, in planets, in your body. Each had to come from somewhere. The Big Bang made hydrogen and helium. Stars make heavier elements through fusion. But no one had worked out the complete account. No one had mapped every element to a specific stellar process. 4 scientists did it. Margaret Burbidge and Jeffrey Burbidge were a married couple, both astrophysicists, both brilliant, working together with a tenacity that is striking even by the standards of post-war science. William Fowler was an American nuclear physicist at Caltech who had been doing exactly the kind of experimental work that confirmed Hoyle's carbon prediction. And Fred Hoyle was still at it, still thinking harder about stellar interiors than almost anyone. Over roughly 2 years, working across Cambridge and Caltech, these 4 mapped the nuclear processes responsible for every element on the periodic table and traced each one back to a stellar source. Their paper was published in 1957 in a physics journal under the title Synthesis of the Elements in Stars. It is known in the field by the initials of its authors, B2FH. What they laid out is, in retrospect, one of the most complete single documents in the history of science. It identified hydrogen burning, the fusion of hydrogen to helium that powers ordinary stars. It identified helium burning, the triple alpha process that makes carbon. It traced the CNO cycle, in which carbon, nitrogen, and oxygen act as catalysts in heavier stars to speed up hydrogen fusion. It described the slow process by which heavier stars fuse carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. And it described what happens when the iron core finally forms and why that matters, which I'll get to in a moment. B2FH also described 2 processes by which elements heavier than iron can be built: the slow neutron capture process and the rapid neutron capture process. and it predicted the environments in which each would occur. It laid out the entire nucleosynthetic history of the universe's atomic inventory in a single, sweeping paper. William Fowler received the Nobel Prize in Physics in 1983 for this work. Fred Hoyle did not. The reasons have never been officially explained. It is one of the more discussed controversies in the history of science awards, and I won't pretend to resolve it. I mention it only because Hoyle's name is inseparable from this work, and leaving him out of the story would be its own distortion. What the B2FH paper gave us is this: a full accounting of where every atom in your body came from, not a rough sketch. A detailed mechanism tied to stellar physics, confirmed by nuclear experiments and by the observed abundances of elements in stars across the galaxy. Before this paper, the question of why gold is rarer than iron, or why silicon is more abundant than fluorine, or why the elements you find in living things are the elements you find in dying stars, that question had no rigorous answer. After B2FH, it did. Every atom of oxygen in your lungs came from a massive dying star, dispersed by a supernova. Every atom of carbon in your DNA passed through a stellar core. The phosphorus in your bones, the sulfur in your proteins, products of explosive nucleosynthesis in massive stars. Your body is, in a very literal chemical sense, the debris field of stellar catastrophes that happened billions of years before the Earth existed. Now I need to tell you about iron, because iron is where the story gets its darkness. Picture a massive star, many times more massive than the Sun, in the last million years of its life. Its core has been running on hydrogen fusion for billions of years, converting hydrogen to helium and releasing energy that pushes outward against the inward pull of gravity. A star is a balance between those two forces, held in tension across its entire lifetime, gravity pulling in, thermal pressure pushing out. When the hydrogen in the core runs out, something has to change. The core contracts under gravity, heats up, and when the temperature climbs high enough, helium begins to fuse into carbon and oxygen. The star reorganizes itself. The new fusion happens in the core. The old hydrogen burning moves outward to a shell. Layer by layer, the star develops a structure like a Russian nesting doll. Different elements burning at different temperatures in different shells, each one deeper than the last and hotter and denser. The progression goes: hydrogen, then helium, then carbon, then neon, then oxygen, then silicon. Each layer burns for a shorter time than the last. The outer layers burn for millions of years. The innermost layers burn for centuries, then decades, then days. The silicon shell at the end, the last stage before the final product, burns for roughly a day. And the final product is iron. Iron accumulates in the core. It piles up. And here is where the star runs out of road. Every fusion reaction that has kept the star alive has released energy. When lighter nuclei fuse into heavier ones, the resulting nucleus is slightly lighter than the sum of its parts. The missing mass is released as energy. That energy is what keeps the star from collapsing. But there is a limit to this, and the limit is iron. Iron has the highest binding energy per nucleon of any common element. What that means is that iron nuclei are, in a sense, the most tightly bound structures that nuclear physics produces. They are at the bottom of the valley. Every element lighter than iron rolls downhill toward it when fused, releasing energy. Every element heavier than iron also wants to roll toward it, but from the other side, and getting there costs energy rather than releasing it. Fusing iron absorbs energy. Fusing iron does not power a star. It drains one. Once the iron core forms, the thermonuclear engine is exhausted. There is no fuel left. And gravity, which has been losing to nuclear fire for millions of years, wins. The core collapses in less than a second. The outer layers, suddenly unsupported, fall inward and then rebound off the collapsing core in a shockwave of incomprehensible violence. What follows is a core collapse supernova, one of the most energetic events in the universe. For a brief time, a dying star outshines the entire galaxy it lives in. And then, in the churning chaos of that explosion, something else happens. the elements that the star spent millions of years building, the oxygen, the carbon, the silicon, the calcium, the iron itself, are thrown outward at a significant fraction of the speed of light, scattered across thousands of light-years of interstellar space. The star is gone, but its atoms are not. They are now in the medium between stars, drifting, cooling, waiting for gravity to gather them again into the next generation of stars, and the next, and eventually, 4.5 billion years ago, into a young star at the edge of the Milky Way, and a disk of debris that would slowly coalesce into a solar system and into a small rocky planet at the right distance from its star, and into the chemistry that, over billions of years, produced the first living things and then more complex things, and eventually something that could hold up its hand and wonder where it came from. If you are looking at your hand right now, you are looking at the ash of dead stars. That is not a metaphor. The calcium in the bones beneath that skin was smelted in an explosion that happened before this planet existed. It traveled through space as debris. It was gathered into the molecular cloud that became the sun. It ended up here, on this small world, inside you. Every calcium atom in your skeleton arrived on this planet the same way. I want to stop on something that the B2FH paper mapped out, but that I haven't named yet, because it bears directly on your body right now. There are 6 elements that make up the vast majority of everything alive. 6. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Scientists use an acronym for them, CNOPS. If you wanted to describe life to another civilization using only chemistry, you would start there. Each of these 6 has a different origin story. The hydrogen, nearly 90% of the atoms in your body by count, came from the Big Bang. It is the oldest material in you, 14 billion years old, give or take. The hydrogen in the water in your cells was made in those first 3 minutes when the universe was a billion-degree forge, and it has been hydrogen ever since. Everything else came from stars. The carbon, the scaffold of every molecule of DNA, every protein, every lipid in your body, was made through the triple alpha process in stellar cores. Some of it came from massive stars and was dispersed by supernovae. Some came from intermediate mass stars that shed their outer layers in slower, gentler ways before dying as white dwarfs. The exact proportions are still debated in the astrophysical literature, and I won't pretend otherwise, but the mechanism is certain. Carbon in your cells is carbon that was once in a stellar core. The oxygen, which makes up roughly 65% of your body mass, came predominantly from massive stars. Explosive nucleosynthesis during core collapse, dispersed by supernovae. Your lungs right now are pulling in oxygen that was made in dying stars. The nitrogen in your DNA's base pairs came largely from intermediate mass stars, the kind that swell into red giants and then shed their outer envelopes as stellar winds before collapsing into white dwarfs. The phosphorus in your bones, the sulfur in your proteins, explosive nucleosynthesis, massive stars, supernovae. And the iron in your blood. The iron in every hemoglobin molecule, in every red blood cell in your body right now, the iron that carries oxygen from your lungs to your tissues, is the final product of silicon burning in a massive stellar core. Iron is what the star was making when it ran out of road. Iron is what accumulated in the core until the star could no longer sustain itself. When the star exploded, the iron scattered. Some of it, after billions of years, ended up here. It ended up in you. You carry the death of a star in your blood. I find myself thinking about that when I'm stuck in traffic, or waiting for coffee. The iron in the hemoglobin moving through my body right now was the element that killed a star. The star had to die to make it, and without it, I couldn't breathe. There is something about that which I don't entirely know what to do with. Now, there was a moment in 1987 when all of this stopped being purely theoretical, when the B2FH model stopped being just a beautiful set of equations on paper and became something you could watch happen in real time. February 23, 1987. A star in the large Magellanic Cloud, a small satellite galaxy of the Milky Way, roughly 160,000 light-years from Earth, collapsed. The event had actually happened 160,000 years earlier, of course. The light was just reaching us now. But from the perspective of anyone alive on February 23, 1987, a star died. And it sent us a message before it even showed itself. About 2 hours before the light from the explosion reached Earth, a burst of neutrinos arrived. Neutrinos are particles produced in enormous quantities during a core collapse. They carry away most of the energy of the event, and they travel at nearly the speed of light. And unlike light, they pass through matter almost without interacting with anything. They pass through 160,000 light-years of space and then through the Earth as if it were barely there. 2 detectors on opposite sides of the planet caught them. A detector in Japan called Kamiokande registered 12 neutrino events. A detector in the United States, the Irvine, Michigan Brookhaven detector, registered 8. 20 neutrino events in total, arriving in a cluster from a point in the sky corresponding to the Large Magellanic Cloud, 2 hours before any optical telescope could see anything. This was the first time in history that neutrinos from a stellar collapse had been directly detected. And the timing, the fact that they arrived 2 hours before the light, exactly as core collapse supernova models predicted, confirmed that the basic picture of what happens inside a dying massive star was right. The explosion was designated SN 1987A. Spectroscopic observation of the expanding shell of gas and debris showed heavy elements being flung outward exactly as the models predicted: oxygen, silicon, iron, the products of decades of stellar burning, now scattered across space. If you wanted to watch the universe manufacturing the raw materials of life and dispersing them into the interstellar medium, 1987 was the year you could do it. SN 1987A is still expanding. The debris field is still moving outward through the Large Magellanic Cloud right now, as you're listening to this. In tens of thousands of years, that material may contribute to the formation of new stars, new planets, new chemistry. Some of the atoms Hoyle described, that B2FH mapped, that the Kamiokande detector caught leaving their origin, some of them may eventually become part of something that wonders where it came from. There was still a gap, though. Even after B2FH, even after SN 1987A, there was one piece of the story that remained unconfirmed, not theoretical, just unwitnessed. Elements heavier than iron, gold, platinum, uranium, lead. The elements that fusion cannot produce, because fusing iron costs energy. If you want to build gold, you need a different process. You need an extreme environment with an extraordinary neutron flux, a place where atomic nuclei can rapidly capture neutrons faster than those neutrons have time to decay. This is called the R process, rapid neutron capture. B2FH described it. It predicted that the R process would require conditions far more extreme than an ordinary supernova. The exact site was debated for decades. The leading candidate for years was neutron-star mergers, collisions between the incredibly dense remnants of dead massive stars. A neutron star is an object roughly the size of a city, containing about as much mass as the Sun, made almost entirely of neutrons packed together at nuclear densities. 2 of them spiraling together would generate exactly the kind of neutron flux the R process requires. The theory said, 2 dead stars colliding is how gold is made. And then, on August 17, 2017, at 12:41 in the morning, UTC, a detector in Louisiana and a detector in Italy, felt the universe move. The LIGO detector in Livingston, Louisiana, and the Virgo detector in Cassina, Italy, registered a gravitational wave signal, a ripple in space-time itself, coming from a point 140 million light-years away. Gravitational waves are produced by massive accelerating objects, and the specific chirp these detectors recorded, a signal that swept upward in frequency for roughly 100 seconds before going silent, was exactly what the models predicted for 2 neutron stars spiraling into each other, accelerating as they approached until they finally merged. 100 seconds. That's roughly how long it took 2 dead stars, each one heavier than the Sun, to complete their final spiral and collide, having circled each other for what was probably hundreds of millions of years. The gravitational wave was followed by a gamma-ray burst, and then, 11 hours later, optical telescopes worldwide found the kilonova, a cloud of newly synthesized heavy elements, glowing. It was located in a galaxy called NGC 4993, 140 million light-years away. The light was gold. Specifically, in the infrared spectrum, the characteristic glow of rapidly decaying R-process elements. Over 100 Earth masses of gold made in seconds in the debris of 2 colliding dead stars. The event was designated GW-0817, and it is the first direct confirmation of a neutron-star merger as a production site for heavy R-process elements. I should be precise here, because the science requires it. GW-070817 confirmed that neutron-star mergers are a major production site for gold. Whether they are the dominant source or whether something else, rapidly rotating massive stars collapsing in a particular way, also contributes significantly, is still actively being researched. The question is not settled as of now, but the fact that we watched gold being made in real time from 140 million light-years away because we had detectors sensitive enough to feel the gravitational distortion of 2 dead stars merging is one of the most remarkable observational confirmations in the history of astrophysics. If you own gold, a ring, a watch, a chain, the gold in it was almost certainly made in an event like the one we watched in 2017. 2 neutron stars, the remnants of 2 massive stars that each ran out of road at their iron cores, that each exploded in supernovae, that each left behind a city-sized ball of compressed neutrons. Those 2 objects found each other across the darkness and spiraled together and collided and produced in the chaos of their merger the material of which your jewelry is made. The gold was made in the death of stars. It traveled through 140 million light-years, or some equivalent distance, over billions of years, until some of it was gathered into the cloud that became the solar system, ended up on this planet, was pulled from the ground, shaped, and put on someone's finger. There is a thread I want to pull now, because it runs through everything I've described and ties it together in a way I think deserves its own moment. The atoms don't stay still. They never have. An oxygen atom in your bloodstream right now did not start there. It did not start in the air. It did not start on Earth. Trace it back. Before it entered your lungs minutes ago, it was part of a molecule in the atmosphere, mixed into the air of the place where you're listening to this. Before that, it was in a plant, exhaled from a leaf, or exhaled by some other organism, or processed through the carbon cycle in some more indirect way. Before that, it was in the ocean, or the soil, or the rock. Before Earth existed, it was in the debris field of a supernova, a cloud of gas and dust drifting between stars. Before the supernova, it was in the core of a massive star being forged. Before the star, it was hydrogen and helium in the dark, slowly gathering under gravity. Before that, it was a proton in a cooling universe 3 minutes after the Big Bang. That single oxygen atom, the one moving through your blood right now, has been on a journey of nearly 14 billion years. It has been inside stars. It has traveled through interstellar space. It has been part of the ocean, probably multiple times, across geologic timescales. It has passed through organisms we don't have names for anymore. It may have been in the lung of an animal that no longer exists, in an ocean that no longer has the same coastlines, on a continent that is now somewhere else. Right now, it is yours. For a while, for a breath. Then you will exhale it, and it will go somewhere else, and eventually, in a very long time, it will return to space. The atom is not yours. You are its current arrangement. The universe assembled those atoms into the shape of you for a brief time, the way a river assembles itself into a whirlpool and then, eventually, smooths back out. You are not the permanent thing. The atoms are the permanent things. You are what they're doing right now. I don't say that to be grim. I say it because I think it is the most honest description of what you are, and because there is something in that description that is harder to look at directly than most of what I've covered so far. The 6 elements that spell most of a human being, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, came from the Big Bang and from dying stars. The hydrogen from a 3-minute window of nuclear physics nearly 14 billion years ago. The rest, from stellar cores and supernova explosions. If you wanted to mail yourself to another civilization as a recipe, most of the ingredients would be star death. You would need the Big Bang for the hydrogen and a sequence of stellar catastrophes for nearly everything else. There are roughly 7 octillion atoms in an average human body, 7 followed by 27 zeros. Nearly all of them, by count, are hydrogen, and all of that hydrogen is as old as the universe. Everything else came from the periodic table as B2FH mapped it, from the stellar processes Hoyle described, from the explosions that SN 1987A confirmed, and from the collisions that G7 watched in real time. Every single one of those atoms was somewhere else before it was you, and every single one of them will be somewhere else after. I want to slow down here and do something that the science invites, but that most explanations skip past. I want to follow one of those atoms all the way through, not abstractly, specifically. Take a carbon atom, one carbon atom. It exists right now in one of the cells of your body, let's say in a molecule of glucose in your bloodstream, being carried toward a cell that's about to burn it for energy. That atom is, depending on when it entered your body, weeks or months or years old from your perspective. But from the universe's perspective, it is very old indeed. It has been carbon for somewhere between 1 and 10 billion years, probably. Forged in the core of a star that died long before the sun ignited, dispersed as gas into the interstellar medium, gathered into a molecular cloud, pulled by gravity into the disk of material that became the solar system, locked into the rock and chemistry of the early Earth, cycled through the carbon cycle for billions of years, moved through oceans and atmosphere, and living things across the entirety of evolutionary history, incorporated into food, eaten, processed, and now, right now, moving through you. That atom has been in more bodies than you can count. Not human bodies necessarily, or even animal bodies, bacterial cells, archaea, the chemical precursors to the first self-replicating molecules in the Archean Ocean, things that don't have names because nothing that complicated was alive to give them one. Your carbon has a history so long that the entire span of human civilization, every culture, every empire, every war, every book, every building, every person who ever lived, represents an eye blink at the end of it, and when you die, the carbon returns. Slowly or quickly, depending on circumstances, it re-enters the cycle. Into soil, into bacteria, into the atmosphere as carbon dioxide, into a plant, into an animal, into the ocean, into sediment, into rock eventually, on timescales that dwarf anything civilization has experienced, back into the crust, back into the mantle, back into the slow geologic recycling of the planet. And in some number of billions of years, when the sun enters its own late stage and expands, and the Earth is either consumed or stripped of its atmosphere, the atoms that were once in you will be released into space, back to where they started. The carbon cycle is usually described as a biogeochemical loop. Organisms take in carbon, organisms die, carbon returns to the atmosphere and soil. That is true and useful and not the whole story. The whole story is that the carbon cycle is just the most recent episode in a journey that started in a stellar core. The carbon in your body is passing through you the way water passes through a cloud. The cloud exists. It is real. It has a shape and a shadow and it falls as rain. But the water was somewhere before the cloud and will be somewhere after, and the cloud is a temporary pattern in a much longer flow. You are a temporary pattern. This is not depressing. Or rather, it is depressing in the way that all true and important things are slightly destabilizing when you first look at them directly. The instinct is to reach for something more permanent. But I keep coming back to the fact that the atoms are what's permanent, and the temporary pattern they're making right now is a person who can wonder about this. That seems to me like the more interesting fact. Carl Sagan understood this. He spent years thinking about it, writing about it, trying to find language that would make the science land in the body rather than just in the mind. Cosmos was published in 1980 when Sagan was in his mid-40s, and it is, at its core, an attempt to describe what it actually means to be alive in a 14 billion-year-old universe. Not what it means philosophically, in an abstract sense, but what the physical facts of that universe imply about the nature of every living thing on this planet. And the line he arrived at, the one that has been quoted and misquoted and paraphrased and put on posters and tattoos ever since, is not poetry. Or rather, it is astrophysical fact, stated as plainly as he could manage. He wrote, "We're made of star stuff, 3 words, short enough to engrave on something, and everything I've described, the Big Bang nucleosynthesis, Hoyle's carbon prediction, B2FH, the supernovae, SN 1987A, the neutron star merger that made the gold, all of that is the mechanism behind those 3 words. All of that is what star stuff means when you actually follow it out." But Sagan followed the thought further than the chemistry, because there is something that the chemistry alone doesn't quite capture, and he caught it in a second line. We are a way for the cosmos to know itself. I have been sitting with that second line for a long time. It is not a metaphor, it is a description of a physical situation. For most of the universe's history, the atoms that make up you were not organized in a way that allowed for awareness. They were in stellar cores, in interstellar gas clouds, in mineral deposits, in ocean chemistry, in single-celled organisms. They had no access to the fact of their own existence. Carbon in a rock does not know it is carbon. At some point, through 4 billion years of evolution on this particular planet, through the development of nervous systems and brains and the specific kind of nervous system you have, those atoms organized themselves into something that could ask where they came from, something that could read a research paper, something that could sit in a room and feel unsettled by the fact that the iron in its blood was once in a stellar core. The universe built you for 13.5 billion years and then, through you, looked at itself. This is one of those statements that can sound like mysticism, but is actually just a description of what happened. The atoms were not aware. They became aware, or rather, they assembled into something aware over the course of cosmic and biological time. The cosmos has, through the specific chain of events I've described, created at least one arrangement of itself that is capable of tracing that chain backwards. You are that arrangement. I want to be careful here, because I don't want to overstate what Sagan's observation implies. It doesn't imply purpose. It doesn't imply that the universe intended to produce something that could observe it. The nuclear physics of the Hoyle state didn't arrange itself for our benefit. It's an interpretation to say so, and not one that the science demands. What the science does show is that the same physics that makes stars work also makes carbon, and the same process that builds carbon builds amino acids, and the same process that builds amino acids, given enough time and enough planet with enough chemistry, builds brains. Whether that's a coincidence or a consequence or something in between is a question the brief is honest enough to flag as contested and interpretation. I'm not going to pretend it's settled. What is settled is that it happened. The atoms assembled themselves, through the processes I've described, into something that can wonder about all of this, and that is strange enough on its own terms without needing to add anything to it. Let me bring this back to something concrete, because I've been floating in the abstract for a few minutes, and the science keeps pulling me back to specifics. Your body is, by atom count, roughly 90% hydrogen. Nearly everything you are, in terms of sheer number of particles, is hydrogen, the oldest and simplest element made in the first 3 minutes of the universe, unchanged since then, just borrowed by successive chemical processes across 14 billion years, until it ended up in you. The remaining 10% by atom count, but the majority by mass because heavier atoms weigh more, is the stellar material: oxygen, carbon, nitrogen, and the rest. These are the atoms made in stellar interiors and dispersed by stellar deaths, gathered into the solar system's formation, processed through the chemistry of the early Earth, cycled through living things, and now sitting in you. If you weigh roughly 70 kilograms, you contain approximately 43 kilograms of oxygen. That oxygen came from supernovae. You contain roughly 16 kilograms of carbon from triple alpha processes in stellar cores, about 7 kilograms of hydrogen from the Big Bang, about 1.5 kilograms of nitrogen From intermediate mass stars and massive stars, the exact split still being worked out by astrophysicists. 1 kilogram of calcium forged in explosive oxygen and silicon burning in massive stars dispersed by supernovae. And roughly 4 grams of iron. 4 grams is not very much, but those 4 grams are doing a specific job. Iron is the atom at the center of hemoglobin. The iron atom in a hemoglobin molecule is what grabs onto an oxygen molecule in your lungs and carries it through your bloodstream and releases it to your tissues. Every breath you take depends on an iron atom that was the endpoint product of a massive star's nuclear burning, the element that forms when a star has no more energy to give, the element whose accumulation triggers stellar death. You breathe because iron exists in your blood. Iron exists in your blood because massive stars made it and exploded and scattered it. Without those stellar deaths, without the supernovae that seeded the interstellar medium with heavy elements, the chemistry that supports your life would be impossible. There's a line between the death of stars and your next breath. It's not metaphorical. It's causal. Here's the part that I keep coming back to, the piece of this story that I find hardest to really absorb. The universe is 13.8 billion years old. The sun is 4.6 billion years old. The gap between those two numbers, roughly 9 billion years, is the time it took to build the material conditions for this solar system to exist. 9 billion years of stellar births and deaths, of the interstellar medium being seeded with heavy elements, of successive generations of stars producing more complex chemistry, until the mix of elements in the molecular cloud that became the sun was rich enough in carbon and oxygen and iron and calcium and all the rest to allow rocky planets to form with the right chemistry. You are the product of 9 billion years of stellar recycling. That's how long it took to build the raw materials. Then add another 4.5 billion years for the Earth to cool, for oceans to form, for chemistry to become biology, for single cells to become multicellular things, for multicellular things to develop nervous systems, for nervous systems to develop into the architecture that produces a self-aware observer. 13.5 billion years of cosmic history. And here you are at the end of it, holding up your hand, made of hydrogen from the Big Bang and everything else from dying stars, briefly organized into something that can trace the chain back to its beginning. The brevity of that is worth sitting with for a moment, not to be morbid, but because the scale of the history is such that your existence, any individual human existence, is an almost vanishingly thin slice at the very end of an enormously long process. The atoms have been on their journey for billions of years. The journey continues after you. What you are is what the atoms are doing now, in this particular configuration, for this particular period of time. And the question that sits underneath all of this, the one I think Sagan was gesturing at, and that the science supports without resolving, is what it means that the universe assembled something capable of wonder. Not just capable of survival, not just capable of reproduction, capable of asking where it came from, capable of doing nuclear physics experiments to figure out why carbon exists, capable of building a gravitational wave detector sensitive enough to feel 2 neutron stars merge 140 million light-years away and measure the gold being made. The atoms that ran the Kamiokande detector on February 23, 1987, catching neutrinos from a dying star, were atoms that had been through stellar cores. The atoms in the LIGO detector that felt GW117081117 were atoms assembled by the same stellar processes that produced the neutron stars that collided. The universe, through the specific chain of events that produced human intelligence and human curiosity, built a machine that could detect its own processes happening in real time. There is no clean word for what that is. It is not mysticism. It is not coincidence, exactly. It's a consequence. It is the thing that happens when stellar material organizes itself across geological time into something complex enough to build instruments. But it is one of the stranger facts I've encountered, and I find I can't hold it comfortably. It keeps shifting when I try to look at it directly. Now I want to go back to something I flagged early on and then left hanging because I promised I would return to it. The gold. I mentioned at the beginning that there was something particular about gold, something worth holding back for the right moment. And I want to deliver that now, not as spectacle, but because it completes the picture in a way that feels important. Gold is useless, in a biological sense. Your body doesn't need it. It doesn't appear in knops. It doesn't show up in hemoglobin or DNA or the lipid bilayer of a cell membrane. It is not involved in any metabolic process that keeps you alive. Gold has no biological function in the human body, and yet people have valued it across the entire span of recorded civilization. Gold crowns in ancient Egypt, gold coins in Greece, gold leaf in Byzantine mosaics, gold circuitry in the device you might be using to listen to this, gold in the rings people put on their fingers to mark the most important commitments they make. Here is where that gold actually came from, not from Earth. Or rather, it came to Earth the way everything else came to Earth. It was in the molecular cloud that collapsed into the solar system. It was in the debris field of dead stars. But unlike the carbon and oxygen, which were made in stellar cores and dispersed by supernovae, processes that happen in single stars, gold was made in the merger of two dead stars. Two neutron stars, the compacted remnants of two massive stars that each ran out of road at their iron cores, that each exploded and left behind city-sized balls of compressed nuclear material that found each other across the dark and spiraled together and collided. In the chaos of that merger, in the extreme neutron flux of two neutron stars smashing into each other, the R process ran. Nuclei captured neutrons too fast to decay. Heavy elements built up in an instant: gold, platinum, uranium, all the elements that fusion cannot make, all the elements that require catastrophic conditions beyond what any single star can provide. Over 100 Earth masses of gold in a single collision that lasted 100 seconds. The gold in any piece of jewelry you own, the ring on a finger, the chain around a neck, was made in a collision like the one we watched in August 2017, 140 million light-years away. Two dead stars found each other. They spiraled for hundreds of millions of years, losing energy as gravitational waves, drawing closer. In the last 100 seconds, they completed their final approach, moving at a third the speed of light. They collided. In the debris, gold formed. That gold scattered into space, traveled through the universe, arrived in the molecular cloud that became the solar system, settled into the Earth, was extracted from the ground, refined, shaped, and placed on someone's hand as a symbol of permanence. As a symbol of permanence, an element made in the destruction of two dead stars in a collision that lasted less than 2 minutes is what we chose to represent the things we most want to last. I don't know what to do with that either. There is a shape to all of this that I've been circling without naming directly, and I want to name it now. Everything I've described, Big Bang nucleosynthesis, stellar fusion, the triple alpha process, supernovae, neutron star mergers, the carbon cycle, is the same process at different scales. It is matter assembling itself into more complex forms, spending energy to do so, and then dispersing again. Hydrogen assembles into stars. Stars assemble hydrogen into heavier elements. Supernovae disperse those elements into space. Gravity assembles the dispersed elements into new stars and planets. Chemistry assembles molecules into cells. Cells assemble into organisms. Organisms briefly maintain their organization against the general tendency of the universe toward disorder, and then they don't, and the atoms return to the cycle. You are part of this cycle, not metaphorically. You are a temporary eddy in a river that has been flowing for 14 billion years and will keep flowing long after you're gone. The river is the flow of matter from simple to complex and back again, from hydrogen to star to heavy element to planet to life, and then, eventually, back to dust and gas and maybe back to hydrogen in the very long run. What makes you different from the river is that you can see the river. You can describe the shape of the eddy from inside it. You can trace the hydrogen in your body back to the Big Bang and the carbon back to a stellar core and the gold in your pocket back to a neutron star merger, and you can feel whatever feeling means at the level of organized matter. Something about all of that. The atoms that make up the instrument of your awareness are the same atoms that have been cycling through this process for most of cosmic history. They are ancient, and they are restless, and they are borrowed. They were in the dark before they were in you, and they will be in the dark again. Right now, though, for this brief window, they are organized in such a way that they can wonder about where they've been. Carl Sagan called that being a way for the cosmos to know itself. I can't improve on that. It is the most honest, short description of what you are that I've come across. So, hold up your hand again. You know more about it now than you did a little while ago. The hydrogen in those cells is nearly 14 billion years old. The oxygen it's bonded to came from a star that died before the sun ignited. The carbon in every cell is there because a quantum resonance in carbon-12 happens to exist at almost exactly the right energy level, a fact deduced by one contrarian astronomer from the sheer circumstantial evidence that you exist. The calcium in the bones beneath your skin was smelted in a stellar explosion. The iron in the blood moving through your veins right now was the element that killed a star. None of those atoms know what they are. They never have. For most of their existence, they were in the dark between stars or inside a stellar core or drifting through a molecular cloud. They had no access to the fact of their own presence. They had no sense of the journey they were on. And then they assembled into you. That is not the end of the story. It is barely a chapter in it. The atoms are passing through. They are borrowing you as much as you are borrowing them, and the loan runs in both directions, and it has a term. You know this already, in some background way you mostly don't think about. What I find changes, having followed the chain all the way back, is the scale. The loan isn't just from the planet. It isn't just from the food chain or the water cycle. The loan is from 14 billion years of cosmic history, from the Big Bang, from dead stars, from collisions between neutron stars 140 million light-years away. The atoms in your hand have been on a journey so long that the entire existence of our species is an afterthought at the end of it. What I don't know, what the science I've described does not settle, is what to make of the fact that the atoms bothered to form something that could notice. Whether that's a consequence or a coincidence, whether it carries any meaning or is simply what happens when hydrogen has enough time and enough gravity and enough stellar catastrophe, I genuinely can't tell you. The honest answer is that nobody can. The question is real. The answer isn't in yet. What I can tell you is that you are standing at one end of an unbroken chain that runs back to the first 3 minutes of the universe. Every atom in your hand has a history older than the Earth. The cosmos spent 13 billion years building the conditions for you, not for you specifically, not with you in mind, but the conditions that make you possible. And now, here you are, briefly at the far end of all that history, capable of tracing it. Sagan said it plainly. We are a way for the cosmos to know itself. Put your hand down, take a breath. The oxygen you just inhaled is on its way to your blood, where iron forged in a dead star will carry it to your cells. The universe is still working. For now, it's working through you. That's enough to sit with for a while.